So we're going to switch over to another DDN and one of our partner presentations, talking a little bit more about how is IME as a burst buffer being implemented. And as we've gone into the deployment of IME in production in the real world, this is a technology I think DDN's been talking about for about 4 years. Now that it's in production, we've learned a lot more about how can we help our users with profiling the I/O of your environments and how we can really target those bottlenecks. So we're going to have James Coomer, who is responsible for our technical teams here in Europe, but really leading our I/O profiling team as well, talk about this project.
Thank you very much. So actually, I'm going to share this little presentation slot with Rosemary, sitting down there, who works for a company we've been talking to for a while, who's been working with a common customer of ours at Sanger in the UK. So she's going to tell us about some work she's been doing around I/O profiling. It's all relevant to us, though, because we've got this new system called IME, and its characteristics are really radically different from conventional parallel file systems. So what you thought was bad or good on a parallel file system may not necessarily be bad or good on IME. It works differently. So firstly, I've got some slides on IME. I'm going to give you an update on that product. Now, it's tough. We've got, I think I just did it in 20 minutes downstairs. So I'm going to try and do it in 10 minutes with you guys. So let's have a show of hands. Who is vaguely familiar with IME? Okay, that's a good start. So this is the problem, of course. We have some compute nodes at the top and a parallel file system at the bottom of the picture. In between, what we don't have is persistent, consistent, beautiful, sequential reads and writes. In the average system, we have a mixture of reads and writes, random I/O, sequential I/O, non-aligned I/O, parallel I/O, high concurrency, etc. And this means that when you buy a parallel file system, you measure the performance with IOR on day one, and you achieve the number you requested, 30 gigabytes a second, 100 gigabytes a second. And then after that, you never see that number ever again, because your applications aren't benchmarks. And the parallel file system, whilst it's got many beautiful things about it, doesn't necessarily handle random and small I/Os in a very nice way. We've got to go undergo quite a complex process to move that 4K I/O or 1K I/O or 1 byte I/O and get it into a file. We've got to somehow do a read, modify, write essentially on a large block of parallel file system space, pull it into memory, modify it, put it back, update the inode, etc. Quite a complex process. And we're also, unless we try and use flash with various cache mechanisms, we're definitely susceptible to the latencies associated with spinning disks. And also, if you've got highly random reads, then it's very difficult to avoid the fact that you can't really prefetch on those extremely random reads. So IME really tries to address all these. And to look at it physically today, what we do is we put a set of x86 servers in between the compute nodes and the parallel file system. So these are going to accept these fragments of I/O from the applications, and then there's some magic that's going to happen, which I'll explain shortly, and then it's going to issue, hopefully as sequential as possible, I/O down to the parallel file system. So not only do we speed up the application's experience, but we also speed up your experience with your parallel file system by presenting it with more efficient I/O. In a little bit more detail, what we really do is we install a set of servers. Today, they're x86 servers with SSDs, NVMe drives, and the 14K. You'll see that downstairs. And we have a number of these on the network. It could be EDR or FDR, or OmniPath, or soon it'll be Gigabit or Ethernet, rather. And we'll also install a small client. So as well as the Spectrum Scale client, or Grid Scaler client, or Lustre client on the compute nodes, we'll also have an IME client. And what the IME client will do is it'll intercept all the I/Os which were intended for the parallel file system, and then send them sideways into this burst buffer. When they get to the burst buffer, we do very little. We write it onto the SSD and make it safe. Now, just to reiterate, what we've done is we've taken some fragments of I/O, and then we've made them safe on the SSDs. There hasn't been this process of putting that into an inode, associating it with doing a read, modify, write, and associating it with a file. We've kept that process of taking the I/O and making it safe in a persistent layer of non-volatile memory. We've made that process extremely quick. I'm going to tell you maybe 3 fun things about IME, some of which I've talked about before and some of which I haven't. So this is one fun thing that you really cannot do with a parallel file system. It's called non-determinism. And the problem with conventional file systems is when you make an I/O, if you were very deep into disks and file system technology, you could predict which magnetic piece of which drive is going to get altered when the I/O hits the file system. In contrast with IME, we can dynamically change our minds on the fly, depending on the current workload, or depending on how the network's behaving, or depending on how the SSDs are behaving. We can change our minds. So in this picture, what we see is each compute node at the top is basically assessing the queue length associated with each of the servers it's doing the I/O to. And based on the queue length, it's changing its mind about where it's going to send that data. So we can smooth out the I/O if an SSD is exhibiting high latency, or a node is congested, or a network is congested. We can non-deterministically move that data away from the problem area. The result of that is what we've seen before. We remove ourselves from the conventional parallel file system problem of Amdahl's law. And what that means is we run at the pace of the slowest element. So with a parallel file system, if a node is going slow, it's misbehaving, or a disk is slow, then generally speaking, the whole parallel file system will run at the speed of that element. With IME, we can essentially redirect the workflow to bypass the problem areas, and then we see this plot here. So when we reduce the performance of one node in our cluster, we go from the perfect ideal scaling line to a slightly decreased one, and it's decreased by exactly the fraction of the system that we've tuned down. Without that, if we have no intelligence in the system, then we see this Amdahl's law curve, a really dramatic decrease in our behavior just because of a small problem in the system. I'm going to switch this one. So one other fun thing that I found out this week, or last week rather, we were in the lab. I'm going to come back to this one in a sec. It's not great to look at this picture, but I'm going to talk you through it, and it is fun when we get to the end of it. We've got 4 slides. So what you're looking at here is our lab system. And it's not the fastest thing in the world. It's just some sort of fairly low-cost third-party nodes. It's just a test system. And what we've done here is we've got a bunch of SSDs. We're looking closely at one of them in the yellow screen over there. And then the top green screen, what we're going to do is we're going to send one offline. So I want you to look at the red circles. Up here is the time. You can see it was last week. And then over here, we're going to offline one of these SSDs in our NVMe system. So it's 10:24 and 42 seconds. I won't show you the video, because even though it's pretty short, it's still too long for this session. At 10:24 and 50 seconds, it's offline and we're rebuilding. At 10:25 and 10 seconds, about 40 seconds later, we're 30% through the rebuild of this 250 gig drive. And then switching forward to 2 slides. We're 100% through rebuilding this drive after about 1 minute and 20 seconds. So it's really very remarkable, declustered RAID, and then we're also taking advantage of the speed of the SSDs and the network to get this about 4.5 gigabytes a second. And as I say, this isn't an astounding hardware system, this is really the software doing this work. So in terms of performance, we've been working with a number of partners. Probably the most important one to date has been iCheck. So Marco's in the audience today. He's been working on our IME system. And what you see here is the results of some of that work happening over the past couple of months. So what you see here is WRF. It's a weather forecasting model, quite complex, quite well used. And what we're doing is we're showing the output from measuring the IOPS and throughput to our burst buffer layer. And then we're going to compare it to looking at the Lustre file system, in this case, performance down here. So here we see, essentially you can look at this line here, and this line here, and this line here. So you'll see we're running in really 3 phases in this picture, and it kind of explains how IME works. So in the first phase, you can see we're doing some very large IOs. So these are something like checkpoints from the WRF code as it's running along. And you can see these spikes hitting IME. Let's look at this case here, and we're hitting 15 gigabytes a second. And remind you, this is a small system. It takes about this much space, so it's not a dramatically large system. On the other hand, when we issue the same I/O, the same benchmark to the parallel file system directly and bypass IME, the burst buffer, then we get much broader spikes, and we're hitting around 3.5 gigabytes a second. So in this relatively small example, where we really limit on client nodes, we're still seeing a 4-fold increase in the performance of this benchmark as we're running these checkpoints. But one of the fun things about this is it kind of demonstrates how IME is going to work, because if you look just after the IME run, there's a little green line up the top here. And what that is is we've issued a sync call. So we're syncing the data that's been issued by WRF and we're syncing it down to the parallel file system. So you can see that data being issued from the IME system and syncing down to the parallel file system right here. So it's a little bit of a demonstrator about how IME works. And it does that in two ways. So the first way is we hand loads of hints to IME, and the more hints we give it, the better behaved it is. And in this picture, you can see that we're giving hints about pre-staging and flushing files between the parallel file system and IME. In this case, it's all policy-based. So the administrator will set some policies, and the IME will automatically flush to and from the file system to maintain a good level of capacity and keep those applications running smoothly. So we must move on very gradually. I'm going to do one more slide on profiling. So I mentioned that the behavior is very different from our parallel file system. In particular, small I/O and random I/O and shared file I/O is extremely well accelerated compared to a parallel file system. So in this case, we're seeing an extremely large example, so a real customer system benchmark. It could be fit into one single rack. The largest file system in the world, or the fastest parallel file system in the world today, is around 1.2 terabytes a second, something like that. This is just about half that speed, but it's not in 30 or 40 racks, it's in a single rack. So we're getting 550 gigabytes a second from a single rack of IME. Most remarkably, though, we're hitting 50 million write IOPS, which is truly very remarkable, and it's really out of the range of any other vendor on the market today. Now here's a contrast. So there we looked at a very large scale system running a benchmark. Here we're going to move towards looking at this I/O profiling. So ourselves in DDN, we're looking at making I/O profiling simpler and trying to make it automated. And we're also working with partners like Rosemary, I'll introduce you to in a minute, looking at how we can make customer workloads and how we can predict how customer workloads can run better with a distributed caching mechanism like IME. In this case, we're seeing one of the key points of IME in action. So here we have a single shared file from many, many threads. And what you'll see is that all the threads are writing to this file. That's the start of the file. That's the end of the file. And we're all writing simultaneously. And what these arrows are down here, that's the very high latency of when a thread gets locked by the parallel file system. And this happens generally with parallel file systems. And then you see the read of the file over here. Evidently, this one's in cache. This is pretty fast. So time's along the bottom, space in the file is vertical. When we run the same benchmark through IME, what we see is this. We totally eliminate this locking process. We allow the code to run at full speed. So instead of taking about 100 seconds, we're taking about 4 seconds for this case. So that's one example of taking a synthetic code and demonstrating how it's going to work when you move from a parallel file system to IME. Now I want Rosemary to come up and tell us about some work she's been doing with Sanger around profiling their codes and seeing, I mean, in our case, we're interested in seeing if they'd be appropriate for IME, but in the general case, we're interested in Rosemary's tools and seeing how they can help us identify good potential customers.